So it's really a great pleasure to have you today. Our friendship goes back many decades, from the early days where we were together students in a Master of Theoretical Physics, and it has lasted ever since. Thierry is a worldly known theoretical condensed matter physicist. He started his PhD at the laboratoire, the famous Laboratoire de Physique des Solides d'Orsay, under the supervision of Heinz Schulz, who has disappeared too early. And actually, in my lecture next time, I'm going to show you some early results of Heinz on the Hubbard model. He has this, Thierry has this fascinating thing that he's both a physicist of quantum systems and a physicist of the statistical physics of classical systems, in particular glassy systems. And he has made very important contributions in both fields, in the field of quantum systems, especially on low-dimensional materials, especially quasi-one-dimensional materials, which will be the topic of his lecture today. But also in the past couple of decades, he has really been one of the most active theorists in the field of cold atoms that I was describing briefly at the end of today's lecture, where he has made wonderful contributions. But he's also the author of really important things in the field of classical statistical mechanics of glassy system. In particular, together with Pierre Ledoussal, he's the inventor of the Bragg glass concept in relation to vortices in dirty superconductors. I'm not going to embarrass him by saying so many other nice things about Thierry, except that he taught me enormous number of things in quantum condensed matter physics when I made myself a transition from classical stat phys to quantum physics. He, after his PhD at Orsay, he went to Bell Labs, the mecca of condensed matter physics at the time, came back to Orsay, and for now several decades he's been a professor at the University of Geneva, Université Genève, and he has had a number of distinctions. He's in particular a fellow of the APS and a member of the French Academy of Science. So without further ado, I leave you the floor, and just a couple of practical things since this is over Zoom. And this is recorded. The recording will be put on the Collège de France website. So if you have questions, please keep them very short during the seminar. We can take a couple of technical, precise, and short questions during the seminar, but at the end, we will have some sort of open discussion session, so keep the longer questions for the end. Thank you very much, and Thierry, the floor is yours.
Thank you very much, Antoine. Thank you for the very, very kind introduction. You made me blush by saying all these very nice things about me. It's a pleasure to be here, even if virtually. I really apologize. It would have been a great pleasure to be physically present in Paris, but unfortunately the quarantine situation when crossing a border would not allow it. So I'm sorry to inflict another Zoom conference upon you. On the other hand, I see that it's also an occasion to see, even virtually, people I could not see in a long time. So this has also some positive aspects. So what I'm going to tell you today is things about the 1D Hubbard model, so the 1D version. It's a little bit putting the roof before the walls, because you don't even know what is the mean field solution of the higher dimensional Hubbard model. So keep what I'm going to tell you in mind, and I hope that you will see the differences with what happens in higher dimension a little bit later in the lecture of Antoine. So before I go to the topic per se, let me show you the family photo. This was a snapshot taken at the start of the confinement, so it's about 1 year old. These are most of the group is working indeed on low dimensional systems, as Antoine was saying. So I'll try to share the excitations that we are having for this type of systems. And I want to point out that, of course, what I'm going to tell today is going way beyond what my own research was, but my own understanding of Hubbard model, 1D systems, and so on, was shaped by many theorists. I've listed some of them in the list here. You recognize Antoine here in particular, but indeed a very special mention must be made to Hein Schulz, who was my PhD advisor, a fantastic physicist, not only in low dimensional systems, but quite generally in all matters pertaining to condensed matter. And I caught the virus of low dimensions through Heinz. Okay, so let's go back to the Hubbard model. We share the same age, actually, 1963. This is the model that Antoine has already presented to you in the two lectures that he gave. It's sort of capturing, it's the Drosophila of strongly correlated system. It's the Ising model of quantum systems, because it contains the essential ingredients. And it's still, it's relatively simple, and we can hope, therefore, to solve it. But what I want to emphasize, and especially in 1D, on what I will tell you, I will, of course, focus on the Hubbard model, but this model has the great advantage to be generic. Namely, if you perturb it a little bit, adding another type of hopping or adding a longer range interaction, most, and of course not all, but most of the physics that I will describe to you today is robust. And that's also what makes the interest of this model, is that it's not a singular point in phase space, and that's something on which we will come back a little bit later. So here is the model written in second quantization. This I refer you to the first lecture of Antoine for this, and I will assume, by the way, in the rest of what I'm going to tell you, that you're familiar, of course, with what you saw in the two first lecture of Antoine, and also that Antoine has introduced already cold atoms and a certain class of experimental systems. So I will go fast. If I'm going too fast, don't hesitate to intervene and stop me, and we will take the time. I've put here a couple of references. Of course, they are totally biased because these are the ones I know best. There is a whole book on one-dimensional systems with a special chapter devoted to the Hubbard model. There is also a whole book devoted to 1D Hubbard model written by Fabian Hessler, which is entirely focused on the Bethe-Ansatz method. This model in one dimension is exactly solvable. So we'll come back to what this means a little bit later. And then I've put more general references here on one-dimensional system. This one is mostly focused on bosons, which is something I will not talk at all today. I had to, of course, make choices, but most of the physics we are going to discuss for the Hubbard model is also applicable for the Bose-Hubbard model, which is the bosonic version, and is also to some extent applicable to spin systems as well. But I will skip all this, and so I refer you to these papers. Okay, before I start, let me just make a 10-second reminder of some of the properties of free electrons in a solid, or what is known as Fermi liquid, which is a brilliant theory by Lev Landau, of what happens when you add interactions on the top of free electrons. So here is the occupation factor, if you want, for free electrons. Every state at t equals 0, every state is occupied below kf, essentially, which defines a Fermi surface. And if you look at the probability of finding a particle with momentum k and energy omega, you will find, of course, that it only exists when omega is equal to epsilon k, the dispersion relation of your free particle, and therefore you find a delta function for the spectral function. I heard the last of the lecture, one was discussing, I mean, I heard a question on photo emission, so I imagine this was mentioned in the present lecture. So this is for free electrons. Now, when you add interactions, indeed, what you could expect is the interactions blurring all these singularities. And one of the big surprises in high dimension was that actually, because of the Pauli principle, this is not true. And what Landau showed is that actually you still get a discontinuity at the Fermi wave vector. This discontinuity is reduced by interactions, but this is the hallmark of what is known as Landau quasi-particle, which are excitations that behave essentially like free particles. And in the same way, if you look at how this spectral function is modified by interaction, you would find that, okay, there is a broadening, there is a lifetime, but the lifetime will become longer and longer as you move closer and closer to the Fermi level, which means that you get sharper and sharper excitations that exist. So this is one of the very important features that has been kind of cornerstone of our understanding of high dimensional systems. And what I will try to convey, one of the message I want to convey today, is that this picture completely breaks down in one dimension, or essentially breaks down in one dimension. And none of what is on the right side here of the screen will stay true. And that makes one dimension special. So there are three myths about one dimension that I want to debunk. The first one is that it's a pure theoretical concept. I'll show you that there are experiments. The second one is that everything is understood in one dimension. I will show you that there are questions we don't know how to solve. And the last one, which is perhaps the most fallacious, is that it's a kind of toy model that you try when you cannot solve the higher dimensional systems. Yes, it has some simplifications, but it has also very distinctive features, which makes that solving 1D doesn't necessarily immediately help you to understand 2D or 3D or 4D. And it has, as I was mentioning, its own physics. Okay, so what is special to 1D? Well, again, as we were discussing before, you see that in high dimension, here I represent particles living in 2 dimensions. Even if you have very strong repulsion or interactions between the particles, like the U of the Hubbard model being very large, then this particle can still sneak around the other particles and in a way not feel very much the interactions. So this is why you can find excitations that sound a little bit like free particles, even when the interaction is very large. Well, if you're in 1 dimension, then you know it cannot work. If you have a line, then if there are repulsion between this particle and this particle, when this one will try to move, it will have to push the next one, which will push the next one, which will push the next one. And therefore, individual excitations cannot exist, and only collective excitation will exist. So what we will see in 1D is that there will be a kind of collectivization of excitations, and everything will be expressed in terms of collective modes. Okay. If you want another picture, I suggest traffic jams on the highway. If you're confined to one single lane, you see that you cannot behave as an individual particle, but you have to follow the flow, and you have to move like a wave of density of particles here. On the contrary, if you can pass, then you can recover some aspect of individual particles. So this would be the crossover between a 1D system and a quasi 1D system, on which we will come back a little bit later. There is a second thing which is a little bit special to 1 dimension, and Antoine already mentioned it for 2 dimensions. is that the lower you go in dimension, the worse the quantum fluctuations and of course the thermal fluctuations become, which means that all the nice theories like mean field theories that we know and love and give usually very accurate answer in high dimension fail miserably usually in one dimension. So for example, saying that you can order the phase of the wave function, which is usually what you do to get a Bose-Einstein condensate, for example, will fail. You will not be able to break the continuous symmetry even at t equals 0. So most of the methods that we are used to deal with in high dimension just go to the garbage can. And that makes, of course, the thing which is especially interesting. We have to develop new methods and new concepts to describe the one-dimensional physics. Okay. The last message I would like to pass before starting essentially the lecture per se is that actually, quite surprisingly, there was an enormous evolution in the last 20 years of the 1D world. Physics is already quite old. I mean, it was already largely explored in the 50s and the 60s with big progress in the 70s. We'll come to that. And of course, a fantastic new concept at the beginning of the 80s. But in the last 20 years, new methods have emerged. Numerical methods, for example, something called DMRG, on which I will come back, density matrix renormalization group invented by Steve White. But also all methods like the Bethe-ansatz, which was the method of solving exactly the 1D problem, in the last 20 years was able to compute correlation functions. So going way beyond what was available before. And this changed a little bit or quite seriously the field. New systems emerged, which were not present 20 years ago, cold atoms that Antoine already mentioned to you, but systems which I will not really discuss today, magnetic insulators, and a lot of also of other systems in condensed matter. And finally, people also addressed new questions that simply were not addressed before, like what happens if you have very strong spin-orbit coupling, which led to the whole field of topological insulators, essentially, out of equilibrium physics, and so on and so forth. So this is something really new, or let's say in the last 15 or so years, and this has led to a drastic change of the 1D world. So I'll try to present, of course, today mostly the ancient physics. I mean, one has to build in order, but I'll try to scratch a little bit some questions which are addressed now and which make the field what it is today. Okay, so how do we treat 1D systems? I told you that the physics, mean field and so on, Fermi liquid and so on, all this was going to the garbage can. And so what methods can one use? And this is a very, I don't want to do an historical, too long historical reminder, but this is a very interesting field because it started to be attacked by a certain number of people using what I would call standard many-body theory technique, so Feynman diagrams, so Tomonaga, Luttinger, and then the Russian school did fantastic studies with Gorkov, Dialoginsky, and my hero Anatoly Larkin, who did fantastic papers using perturbative calculations resummed to all orders in many-body physics. But clearly, this was really forcing a tool which is not adapted to tackle this kind of physics. But despite this, enormous progress was made in this direction. Then 1D physics is blessed by the fact that some models are exactly solvable, and the idea of this solution was introduced by Hans Bethe 90 years ago. We are very close to not too far from the 100th anniversary of the Bethe-ansatz. Now, when you see that some models are exactly solvable, so for example, the Heisenberg model, the Hubbard model, the version of the Hubbard model in the continuum, which is called the Godin-Young model, and so on, are exactly solvable. What does it mean? Usually it means that you can show that the model is exactly solvable. That's it. But you don't have any idea of the solution. then it means you can solve the problem on a discrete system of finite size. Then, working harder, you can solve the thermodynamic of the problem. And as I said quite recently, and only for 2 models to the best of my knowledge, which are the Lieb-Lininger model for bosons, the version of the Bose-Hubbard, if you want, for bosons, and the Heisenberg model, could correlation function be computed. Nevertheless, so here I'm showing Hans Bethe and one of the Pope of Bethe-Ansatz, which is Elliott Lieb. Nevertheless, this allowed to make fantastic progress as well. For example, the fact that the Hubbard model has a Mott transition at half filling was, to the best of my knowledge, shown first by Bethe-Ansatz in a famous paper by Elliott Lieb. Really proven, nicely done. Okay, now what can we do? We don't want to use perturbation, many-body theory, and so on. We can do field theory, and there are techniques. I will explain a little bit a technique known as bosonization. There are very powerful technique known as conformal field theory. And essentially, the people who did a fantastic job in this direction were Alan Luther, the late Vic Emery, and closer to us, Duncan Haldane, who got the Nobel Prize for some work on spin chains, topological work on spin chain, but could easily have gotten it for what he did also on 1D, in particular, introducing a concept that I will discuss, which is known as Luttinger liquid. And then you have numerical techniques. So of course, there are the conventional techniques, Monte Carlo and so on, but there was a particularly powerful technique which was developed in 1 dimension called density matrix renormalization group by Steve White in the mid-90s. And around 2005, there was a revolution in this field with 2 groups, the group of Steve White and Adrian Feguin, and the group of Uli Scholvok and Corinna Collat, who was doing her PhD in Uli's group at the time, developed or extended the DMRG to the possibility to compute time-dependent correlation, which opened the way to treating finite temperature, to do out of equilibrium, and so on and so forth. So again, something which was already present in the 90s, but in just for ground state and static correlations, which completely exploded 15 years ago. Now, each one of these techniques is interesting in itself, but each one suffers from limitations. Exact solutions are limited to exactly solvable model, and you never know whether the solution you will find is generic or not generic. And you also never know usually how to compute the correlations. The field theories are very nice, but they are limited to large distance, low energies, asymptotic properties of the system. And when you want to compare, for example, to cold atoms, it's not necessarily very efficient. Numerics is very nice, but it suffers from the opposite limitation. It's valid at short distance, short time. And then if you want to go to very long time, it's difficult to put in play. What is remarkable in 1D, and so far, I don't think the same has been accomplished in higher dimension, despite important efforts, is that people manage to make these 3 techniques work together. We now know how to input things from the Bethe-Ansatz solution or the numerics into the field theory and transform the field theory into an essentially exact technique, which will not only be valid asymptotically, but will be valid up to relatively short distance. And then for the rest, the numerics take over, or the Bethe-Ansatz takes over. So if there is a take-home message of this lectures, is just of this lecture, sorry, seminar, is just that one thing which was instrumental in making huge progress in 1D was to have these 3 aspects work together. Okay, now let me start the lecture per se and tell you a little bit how we solve. I won't go too much into the details, but I want to give you a flavor. So the trick is to try to re-express all the excitations in terms of collective coordinates, because individual objects, C dagger C, creating particles, are not good excitations. You have no chance to get your Hamiltonian diagonal in this excitation. So how it's done, let me just say it very briefly. You introduce a field which is labeling the particles. So you want this field to take integer values at the position of the particle. This is a trick that was invented by Duncan Haldane, and we generalize methods that were developed again starting in the 50s and with big expansion in the 70s. So you want this field to be 1 at the position of the first particle, the position of the second, it's 2, and so on. And you see that in 1D you can do this because you can order the particle from left to right, which is not something you can do in more than 1 dimension. Now, by distorting this field, you can put the particles wherever you want. Okay, so this is a faithful expression of the system. The idea is that this field will have a smooth limit even if the density of the particle is extremely singular, because it depends precisely where the particle is located. So the idea is to construct a field theory using this smooth field as sort of the essential component of the field theory. Think of the deviations of this field to a straight line as the displacement in an elastic theory. So you can think of the deviations from the straight growth of this field as simply the displacement. So by simple manipulations, you can re-express the density in terms of this displacement field here, phi, with, let's say, respect to the average density of particles, which will give a finite slope to position the particle regularly. And you can re-express the density of particles as a kind of very complicated sum here of harmonics of the average density of particles. What you do here is a Fourier decomposition of the density. Again, think of this field phi as the displacement compared to a crystalline arrangement. Of course, you don't want to describe a crystal, but you can start with a crystal as your kind of basic position of the particle. And then this field phi is telling you where to find the particles compared to this. So you get long wavelengths distortion of this crystal, which are usually what you write in an elastic theory, the gradient U, the divergence of U here. And then you get harmonics, which tells you that your density has oscillations which vary with the average density of particles. So this is a representation. Now, this representation is fine, but whether it's useful is a different story. And to cut a long story short, it's an extremely useful representation because introducing this field phi and introducing another field, which is, oh, sorry, I should have written it, which is the phase of the wave function here, you can completely re-express the single particle operators in terms of these two collective objects. One is a field which will tell you, which I call phi, which will tell you when the density is ordered, when the density is, if this field was ordered, the density would be well defined. And the other is the phase of the wave function. And if this field was ordered, you would get superconductivity or superfluidity. Now, of course, as you can guess, these two fields are canonically conjugate and they cannot order simultaneously. You see that in the decomposition of the density, you get these harmonics. And it means that you always have, if I take p equals 0 here or p equal -1, you will always have oscillations here in the fermionic field. And this is what you expect. Oops. This is what you expect if you have a Fermi surface in one dimension, because the particles which are close to the two Fermi points are close to plus kf and minus kf. And you can easily convince yourself that pi rho 0 is kf in one dimension, that this is just describing actually the fermionic fields close to plus kf or close to minus kf, which people call right and left movers in one dimension. Now, I can compute correlation functions of these objects. I just show you here, I'll come back to that in a moment. I just show you here some correlations. You see already something very weird is that the correlation will have oscillating factor, but will behave as Paolo. I will explain in 1 second what is this parameter. But what is important is that because of this weirdness of collective fields, for example, the discontinuity that you would get at the Fermi level is gone and is replaced by an essential singularity. So you lose completely the individual character of excitations that you would have had in higher dimension. So let me give you, in terms of these fields, the Hamiltonian of the Hubbard model in a way you have not seen before. Of course, I can introduce a field for spin up. I can introduce two fields, phi and theta for spin down, and I can make linear combination. Phi up plus phi down, I'll call phi rho, and phi up minus phi down, I'll call phi sigma, and same thing for theta. Here is the Hubbard model rewritten in terms of these fields. You notice two things. The first one, the Hamiltonian is now completely decoupled into two sectors. One which contains only the rho field, which is phi up plus phi down, and one which contains only the sigma field, which is phi up minus phi down. This is totally surprising because it means that the sector which I call rho doesn't know what the sector which I call sigma is doing. I've split my Hilbert space into two separate Hilbert space, one concerning the charge degree of freedom and one concerning the spin degree of freedom. And that's something called spin charge separation, which is specific to 1D and on which we'll come back. The second thing which is remarkable is that this Hamiltonian have essentially an harmonic oscillator structure. Pi is the momentum conjugate to phi, and pi is essentially the gradient of the field theta that I introduced before. And you see that here, all the interactions seems to have disappeared. The U of the Hubbard model seemed to have disappeared. Actually, it has not disappeared. It's hidden in the coefficients here, which are the coefficients of this harmonic oscillator Hamiltonian. Let's forget the cosine for a while here that appear. This is a remarkable result because if there was not this cosine, what you would say is that you have a quadratic Hamiltonian. So I've diagonalized for you the Hubbard model. I've made the interaction disappear. Why? Because the interaction is density, density, and density, density is grad phi, so it becomes again a quadratic term. So this is the wonder of this technique, which is called bosonization, which is an historical name, in the sense that it allows to diagonalize very easily the 1D Hubbard model. And the interactions just play a role as a coefficient in this harmonic oscillator Hamiltonian. Well, you see that the thing is not just trivial here. There are two additional terms which appear, which are a little bit nasty, which have the form of cosine. So actually, this is known as the sine-Gordon Hamiltonian, but this is also an integrable model that people know how to solve. I just want to point also the symmetry that exists between these two Hamiltonians. And this is the consequence of the particle Hall symmetry on one sector that Antoine was telling you during the first lecture. You see that I can exchange the charge and the spin sector if I exchange the chemical potential with the magnetic field. And it's apparent here directly on this bosonized form that actually these two Hamiltonians are in the charge and the spin sector are similar. But this tells you more. It tells you that here you separate your Hilbert space into two parts. This term you can forget if you're not at half filling, if the chemical potential is not zero. And trust me, for the moment, we'll forget this term. We'll come back to it when we have to discuss a negative U Hubbard model. But for the moment, let's just remember the quadratic Hamiltonian. A consequence of this is that I can compute all the correlation functions. And as I was mentioning, now you know what these parameter K are. As a consequence of this, you see that correlation function dk has non-universal power laws with an exponent which is controlled by the interaction. So here K is essentially K rho if you want. So this is one of the remarkable facts of 1D physics, is that the system is kind of poised at a critical point. You know, usually when you get power laws, it means you're at a special point. You're at a critical point. Here, you're always at a critical point if you want. So your system has these very slowly decaying correlations. It's not ordered. It cannot order, but it would like to order, and it therefore has power law decay of correlation functions, which means the system will be extremely susceptible to perturbations. Okay, let's move forward. And first, you could say, oh, look, it's very nice what you write, but for example, here, the ratio of U sigma divided by K sigma. So you see that U sigma is as the dimension of a velocity. It's the velocity of spin excitation. U rho as the dimension of a velocity, it would be the velocity of charge excitation, and K, the K's are dimensionless parameters, which, as I was mentioning, control the decay of the correlation function. But you can clearly see here that if the expression that I was writing were correct, I would get a very serious instability when the U of Hubbard is too large. This would become negative and I would get an instability. So actually, this expression are straightforwardly perturbative. I just sort of replace the expressions that I was giving you of the single particle operator, throwing half of them away and writing this quadratic Hamiltonian. And in the 70s, people were kind of wondering how much of this is robust, how much of this would survive if I want to go to large U. And there was a big surprise that came with Duncan Haldane at the beginning of the 80s, where Haldane said, no, nothing that is discussed so far is perturbative, provided you use the correct velocity and the correct parameter K. So these expressions are wrong, but this object here is correct and represent, if you want, a fixed point, which will describe the low energy physics of the system. So this defined a whole set of properties in 1D, which went by the name of Luttinger liquid. And as Fermi liquid was not due to Fermi, but to Landau, Luttinger liquid is not due to Luttinger, but to Haldane. And this is a kind of generic physics that encompasses spins, bosons, Hubbard, extended Hubbard, modified Hubbard, and whatever. And the difficulty is mostly to be able to access these parameters. How do you access them? Well, you take an exact solution of the problem, either from the numerics or from the Bethe-Ansatz. And you extract the parameters from the numerics, then inject them in the field theory, and you get an essentially exact field theory. So this was an extremely powerful tool that Haldane was giving, because now we could study the Hubbard model with U equal 1 million without problem, provided one extracted the correct Luttinger liquid parameters. So for the Hubbard model, this was done by Heinz Schulz, and I reproduce here his results. I won't go too much on the parameters themselves. They are not super interesting by themselves, but you see that as a function of the density, one can extract the parameter K rho. One can extract the charge velocity here, which are represented for various interactions, and the spin velocity. You see that when the density becomes close to 1/2, the charge velocity collapses and goes to 0. This is because the material becomes a Mott insulator that I'm sure Antoine will talk about. And the spin velocity goes to a constant because you get super exchange between the spins, and you can extract it. These parameters were computed from the Bethe-Ansatz solution of the Hubbard model. Okay, for the attractive Hubbard model, one can do the same thing. We did that with Shriram Shastri. Again, it's nothing specific that I want to discuss at that stage on the parameters, but something on the Hubbard model. This coefficient here is U. When U is positive, you can check, and I won't go too much in detail, that this cosine here is irrelevant. So it disappears, and the spin sector is massless, and is describing the spin fluctuations that we know and love of an antiferromagnet. I'll come back to that. But when U is negative, this cosine is violently relevant, and it orders the field phi sigma. So it opens a gap in the spin sector, and of course, this gap corresponds to the pairing that exists in the Hubbard model. So you see from this Hamiltonian, and you can study from this Hamiltonian, the passage from a repulsive antiferromagnetic system to an attractive paired state. What is the charge physics? We have to determine from the other part of the Hamiltonian. Okay, let me discuss a little bit the consequences. Power law correlations. Here are the density-density correlations for the Hubbard model. There are logarithmic corrections that I don't want to discuss. Spin-spin correlations are decaying as power laws. So you see that this Hamiltonian, the Hubbard Hamiltonian for repulsive U, is essentially describing an antiferromagnet with spin oscillations at the density. So if you're at half filling, density is 1/2. This is an antiferromagnet with commensurate spin oscillations, plus minus, but the spin is not ordered and the correlations decay as power laws. Same thing for the density. The charge density is oscillating and decaying as a power law of the distance. One can write a kind of generic phase diagram by looking at what is the correlation that decays the more slowly. And the Hubbard model is along this line here. This is the repulsive part of the Hubbard model. It's dominated by spin correlations, spin antiferromagnetic correlations. And when you go to the attractive Hubbard model, you find that there is a gap which develops in the spin sector, which is the pairing. And then the dominant correlations are not spin-spin or density-density, but are actually singlet superconducting correlations. So pairing is the dominant correlation with the slowest decaying exponent. So you can get a physics which is, I would say, relatively familiar and relatively similar to what you would naively expect in higher dimension, except that instead of having ordered phase, you get these power law quasi-long range order phases at zero temperature. Things start to get a little bit weird if you look at the spectral functions, because remember that we get these two sectors, one with a velocity u rho, the other with a velocity u sigma. So the spectral function, the probability to find a particle with energy omega and momentum k, now doesn't have a single peak. It has actually two peaks. And this was worked out by, in particular, Johannes Voigt. And these two peaks reflect the two velocities that you have in the problem. So you start seeing that you won't have lambda quasi-particle in this system, but you will get two power law singularities, essentially, around the two velocities. So, okay, let me skip finite temperature so that just to say that at finite temperature, all correlation function decrease exponentially. Now, the fact that you can decompose your Hamiltonian into two sectors, this is the signature of spin charge separation, which means that the charge degree of freedom don't know what the spin degree of freedom are doing. Let me give you a little cartoon. Let me remove here an electron in the 1D Hubbard model. I just choose one particle per site, and I remove a charge and a spin. But then I can let the spin flip by super exchange. And I will move the spin excitation that I have created somewhere else in the system. And this will create a place where I have two spin down which are close to each other, but you see that no charge is missing. So this is an excitation which is described by the rho part of the Hamiltonian. The sigma part of the Hamiltonian. This is what people call a spin-up. You can do the same thing by letting the particle move. And you see that after a while, there will be a place where there is a charge missing, but the antiferromagnetic arrangement down, up, is still there. So there is no spin missing, but there is a charge missing. And this is a particle that people call the holon, which is described by the rho part of the Hamiltonian. So you see that in 1D, the electron will deconfine and decompose into excitations which carry less quantum numbers, which is highly unusual. In higher dimension, the only example I know are Laughlin quasi-particles, which carry 1/3 of the charge of the electron. Here, you see that you have one excitation that carry the spin, but no charge, one excitation that carry the charge and no spin. And of course, they can leave because of this collective they are collective excitations. If you try to do the same thing in higher dimension, it doesn't work. At least it doesn't work naively. Let's try to do the same thing. I remove one particle, and now I flip my spins. Let me accelerate the motion. You see that here I have a lot of places where I have now 3 spin down and 3 spin up. So if I have an antiferromagnetic superexchange, it's not very favorable for the system. Same thing, if I move the particle, I will do the same. So you see that if I was thinking of doing the same thing, the presence of the other chains here, the fact that the system is 2D, will create a string between the hold-on and the spin-on, whose energy will grow with the distance. So these 2 particles are confined, and therefore they form a bound state, which you could call a lambda quasi-particle. So at least naively, this deconfinement mechanism only works in 1D. Of course, it's a big challenge to try to find ways to get this deconfinement mechanism or similar deconfinement mechanism to work in a higher dimension. Okay, so this is one of the peculiarities of 1D world. I won't mention at all the topological nature of these excitations. I refer you to this article in this book if you're interested in it. Topology is the norm in 1D. It's very difficult to escape. You look at the values of the fields at -infinity and +infinity. You see that there are cosines in the Hamiltonian. So it means if you want to stay in a minimum of the cosine, you can only take discrete values, and you can very easily define topological indices. But I won't discuss this much more in detail. Let me move to experiments. First, what is 1D in the real world? Of course, we live in a 3D world. So there are 2 ways you can realize a 1D system. The first one, you confine one of the direction so hard that because of the confinement here, the energy levels are relatively continuous with the quantum number in this direction, but are very discrete with the quantum number in this direction. So you would get 1 milliband here, another milliband here, and so on. And if the temperature or the interactions are not able to provide the energy to go from this milliband to this milliband, you see that you get a system which is quantum and whose only degree of freedom that can vary are the longitudinal degree of freedom. The other are completely frozen, and therefore that's a 1D system. The other possibility, which is realized in a form, for example, of organic conductors synthesized by Klaus Beckgaard and intensively studied by Denis Gérôme, who discovered superconductivity in these materials, is that you have many 1D chains. Here you see a chain perpendicular to the screen, and the hopping of the tight binding between the plates, which are stacked on the top of each other, and the next column are very, very anisotropic. And so here it's essentially 3000 Kelvin along the stack, 300 in one direction and 30 in the other. So if you manage to be at an intermediate temperature range, you cannot have coherent hopping from one chain to the next. And again, you're in a 1D regime. But there, when you will lower the temperature, the material will get a dimensional crossover from 1D to 2D, then 3D. And actually, a lot of interesting physics in this material happens at very low temperature, in particular superconductivity of a nature which is still unknown. And this is definitely happening when the material is not anymore in its 1D range, which is somewhere here at high temperature. Okay. Test of power laws. There are several tests of power laws. I will go very fast because the goal is not to do in the organics. You can measure, for example, the optical conductivity. Theoretical prediction would give you a power law, and lo and behold, over a decade, which is sandwiching between the bandwidth and the material and the energy of the hopping between the chains, because otherwise you cannot use a 1D theory, you see a very nice power law, which is, I think, to the best of my knowledge, the first observation of a Luttinger liquid power law in a metallic system, in an itinerant system. Nanotubes were also advocated as showing these power laws. Here are experiments showing the conductance in a nanotube as a function of temperature, where you see clearly Paolo behavior. And more recently, so this is not the Hubbard model, but this is bosons, but such Paolos were also observed in the cold atom context in Jörg Schmidt-Meyer in Vienna's experiment by interfering two tubes of atoms, which gives you access to this correlation function, which for bosons is a simple Paolo. And the theory was done by the late Adilette Imambekov, Gritsev, and Demler. And lo and behold, you see things which are well compatible with the scaling, with the size, with what you would expect for a Luttinger liquid. You can also test that you control reasonably well the calculation of these parameters. Again, I'm slightly cheating. It's not the Hubbard model. It's the continuous version of the Hubbard model known as the Godin-Young model. So there is no lattice, if you want, along the tube. These are experiments done in the group of Randy Hewlett with two species of fermions. And using a Bragg spectroscopy technique is measuring the density-density correlation function, which should have a maximum when omega equal VQ. And we could compute the velocity. The model is integrable, so we know the velocity. And with a little bit of massaging of the data to take into account the complications of the experiment, like the confining potential and so on, you see that we have a very good agreement between the theory and the experiment on the way this velocity varies with the interaction in the system. So okay, let me pass this. One can even do quantitative tests. I don't want to go too much in this because this is not the Hubbard model, but just to say that using this combination of extracting the Luttinger parameters from the numerics, injecting them in the field theory, and playing also with things that I didn't discuss, which are the prefactors of all these Paolos, which we also know how to extract from the numerics, you can do a quantitative test without adjustable parameter of this theory. These were experiments done in the group of the late Claude Berthier in Grenoble by Martin Klanczek, and we did the theory. This is Pierre Bouillot and Corinna Collat. And let me just show you the data. This is the nuclear relaxation time on spin ladders. And you see here the data points. The red curve is a theory curve which was entirely determined without any adjustable parameters. So this is something which is, for me, quite remarkable, because combining numerics and field theory, we are now able to make really quantitative predictions of this Wendy physics. Let me skip this. In similar systems, Andrei Zeludev was even able to test the scaling of this correlation. So here is, for example, the scaling that you would expect of these Paolo correlations, which have, of course, a scaling as frequency divided by temperature. And the experiment and the theory are in remarkable agreement. So this is all good for the Paolos. Now, if I go to spin charge separation, this is much less fun. There are some photoemission experiments which showed, I would say, good evidence of spin charge separation, but it's very hard in condensed matter to nail it down cleanly by a photoemission technique. Again, maybe professional photoemission would disagree with me, but for me, my eye has a little bit of difficulties with this. The most beautiful experiment, to my knowledge, is the one performed in Amir Jacobi's group, where he did tunneling between two quantum wire, and the theory was done by Tcherkovniak and Bert Alprin. And he could see, okay, you could discuss whether you see the two modes here corresponding to the two velocities. When the particle tunnels, it has to recompose, so it has to contain the information on the two velocities. But they could do a kind of interference experiment using the finite size of the wire here, and they see a moire pattern which traduces the beating, the interferences between these two velocities. Where spin charge separation is concerned, cold atoms were really nice and provided very beautiful tests of this. So here are experiments done by Guillaume Salomon, in particular in the group of Emmanuel Bloch, where they realize 1D Hubbard chain, but they have a microscope. They can take a snapshot of the chains and tell you exactly where are the spin up, where are the spin downs, where are the holes, and so on. And so what they see is that if they squeeze the hole, they get nice antiferromagnetic correlation, which is exactly the picture that I showed you. When you get a hole on, it's surrounded by up and down, but it pushes the spins. So it means it shifts the antiferromagnetism. So you would lose rapidly the apparent antiferromagnetic order. But if you remove the holes, you see that you recover a perfect staggered antiferromagnetic order. They could also go to the doped Hubbard model and test indeed the spin charge separation. Here is a schematic, but this is actual data, where you see that you get a spin down, a hole, then a spin up, as it should around the hole on, then a spin down, a spin up, a spin down, a spin up. So this is totally confirming the little cartoon that I was showing you before on the physics of this spin charge separation. Maybe I'll skip the mod transition. It's a fascinating subject in 1D because it's connected. So Antoine has not yet told you that at half filling, the system is an insulator, that it has antiferromagnetic order, and so on and so forth. And in 1D, it's a fascinating subject. So let me skip this for two reasons. The first one, the mod transition occurs regardless of the strength of the lattice. So you don't need to be in the Hubbard limit to get a mod insulator. Any tiny lattice will realize it, will do it. The second, it's connected to a beautiful transition, which is the Berezinski-Kostelis-Thouless transition. So the mod transition in one dimension is the analogous of the Berezinski-Kostelis-Thouless in 2 dimensions. And actually, you can test predictions of BKT by looking at quantum systems in 1D. And this was done with cold atoms, but I won't have time to tell you about it. Just to say that one can test some of these predictions in relatively sophisticated transport experiments that were done in the group, this is Martin Lebrun in the group of Tillman Esslinger, where they were able to realize big reservoirs here of atoms, 2 species, and then put a periodic lattice here to do a 1D channel. So this is not a Hubbard model. This is a model where the lattice is not infinite, if you want, but you can study transport through this thing, and you can test some of the predictions that I was mentioning before. Let me skip this and try to use the 2 minutes that I am left to go beyond 1D to tell you a little bit some maybe more actual questions. So you see that in 1D, we are in pretty good control. The thing that remains to be understood is, of course, out of equilibrium, transport, and disordered system. These things, even in pure 1D, are still resisting, and there is a lot of things to do in this direction. But where the frontier really lies is in trying to go beyond 1D, coupling chains, and trying to go the other route to approach 2D or 3D out of this 1D physics that we understand. The first element on this is ladders. You can take 2 Hubbard chains and couple them by hopping. And there you have a big surprise. I don't want to discuss much more, that the antiferromagnetic phase of the Hubbard model is replaced by a D-wave superconductor. So a 2-leg ladder is completely different from a single leg. And instead of being antiferromagnetic, is superconducting, entirely mediated by repulsive interactions. This is a remarkable prediction, and testing it is, of course, difficult. Experimentally, I don't know any test of this. Numerically, there were a lot of studies in the mid-90s using TJ ladders, but only recently, I refer you to this paper by Matthias Streuer, only recently could people really study Hubbard ladders and nail down the fact that indeed this prediction is correct. And then you can have fun. You can, when you have these ladders, for example, one question we are trying to have fun on is, what is the Hall effect on this type of systems? Because Hall effect, when you have interactions, is not really understood. So here is some study we are doing with Sebastian Grechner and Michele Filippone. And you see that we're trying to pass a current here and look at the accumulation of charges on one side of this ladder. Let me skip this. Cold atoms are realizing this. They're realizing these ladders and they are studying Hall effects. So no, I'm not rushing, but I'm close to the end. Don't worry. They are realizing these ladders, and we hope to have comparison with, for example, the Hall effect. Now, the real question is, of course, in connection, especially with what Antoine is telling you, is what happens when we will have many chains. And as I was mentioning, this is directly relevant to study the physics of some of the compounds, like the organic conductors. Indeed, when you lower the temperature, you go from a 1D regime to a 3D or 2D regime, and you can study this regime by varying the temperature. It's extremely difficult to put back the hopping because it's a relevant perturbation. This was first determined by Claude Bourbonnais in Sherbrooke. And essentially, it spoils all the nice 1D physics that we are discussing. And unfortunately, when we go to 2D, we're also having problems to do the study. So for the moment, the question is open. We expect some phase diagram of this form where the system will go from a Mott insulator, for example, in 1D, and then you increase the hopping between the chains, and at some point you will go to a high dimensional metal. And there is some evidence in these organic materials that such a phase transition is observed. Here are resistivity measurements done in the group of Denis Jérôme, which show evidence that there is an energy scale going down to zero at a certain pressure, which means a certain transverse hopping. But studying this quantitatively is very, very difficult. We did some attempt together with Ilke Biermann, Antoine, and Christophe Berthaud, trying to use dynamical mean field theory and saying, let's treat one chain exactly, but view the rest of the universe as a bath. And this provides interesting solutions. Okay, here are some curves of the quasi-particle residues that were obtained. We observed sort of pockets on the Fermi surface of this material, but it's very difficult to keep this method under control. So for the moment, I would say this problem is very, very seriously resisting study. So I'm more presenting this as a teaser to say that one needs if one wants to crack this problem, one needs a good idea. Same thing goes if one tries to start from the 1D study. I show you that this DMRG technique is working very well in 1D. Unfortunately, if you try to extend it to more and more legs, this is getting increasingly difficult. You recover an exponentially growing time. Here is a recent work we did with Adrien Cantillon, Michele Dolfi, and Matthias Streuer, trying to sort of brute force address what would happen in a 2D system by extrapolating what we have for a certain number of coupled chains. This is not exactly Hubbard chains, it's an extended Hubbard model, but the idea is the same. One important question is whether we would retain a spin gap in this system. And okay, extrapolations are very, very difficult to do. But at least what we seem to find is that the spin gap would survive, indicating that for this system, the 2D regime is also an anomalous regime. But these are clearly works in the making. These are clearly works which do not give the ultimate answer. And this is also where the border is, what will happen when we start coupling chains, either in a finite number or going to the infinite number of chains. Okay, I think my time is up. It's time to conclude. So I just took you on a little tour of Hubbard model, or more generally, the one-dimensional physics, because as I said, it's quite generic. I, of course, presented more the old results, but it's a field which is quite active with a lot of questions. If you have something to remember, is that the Luttinger liquid theory provides a framework to study this physics, but more importantly, to go way beyond, couple chains, put disorder, study out of equilibrium physics, put a gauge field, and so on and so forth. And of course, there we don't have the answer. There are beautiful and challenging questions beyond the simple physics that I presented you. What is important, I think, is that what cracked the problem is this interplay of analytical and numerical techniques that were needed to make progress. And finally, there are many, many experimental realization, which is extremely stimulating for the theorist, but sometimes, of course, put also a little bit of pressure on us. And on that, I will stop and thank you for your attention.